In this video, we are going to derive the equation for centripetal acceleration for an object moving in a circle. I've already stated that the radial acceleration is equal to v squared over r. So that's what I've stated already. I want to prove that that's true, and we're going to use a really great geometry proof to make that happen. Remember that our definition of acceleration in general is a change in the velocity vector over time, and here it's the direction part of this velocity that's changing. So we're going to need to draw out some vectors to really see what a change in velocity looks like even at a constant speed. So here's the picture. It's moving in a circle. Velocity is tangent to the circle. Our initial is directly up toward the top of the screen. Our final is sort of in an up and to the left direction. And the radial acceleration must point in toward the center of the circle, as we may see later on. And what I want to define here is this angle theta, which is the angle that the initial and final subtends as it goes from that initial to final state. So let's go ahead. I want to draw a picture. The picture I want to draw is my initial velocity arrow and my final velocity arrow starting at the same dot. So I'm moving those vectors along. And they have been displaced, so that means that our change in velocity from initial to final looks like this. That's our change in velocity arrow. Because this is the end of the initial arrow, it's the end of the final arrow. That's what the change in velocity would look like. And because the whole picture has been rotated by an angle theta, the angle between the initial and final must be that angle theta. Now, let's look at a similar triangle. But the triangle I want to look at now is the radius vector. And so I'm actually going to erase these radial accelerations and move them inwards. So I'm going to look at the vector that starts here. So that's our initial position vector if we're looking along the radial direction. And right here is our final position. And I want to draw that triangle next. And so our initial radial arrow looks like this. Our final radial arrow looks something like this. And the initial to final arrow, the change in direction, that displacement, looks something like this. And again, as we can see directly from the picture now, this is that angle theta. Now, here's where the geometry comes in. We have these two sides. This is an isosceles triangle, right? The speed isn't changing. Similarly, the radius here, this triangle is an isosceles triangle because the size of the radius of the circle isn't changing. And so these are isosceles triangles which share an angle between the two congruent sides. As such, the velocity triangle is similar to the radial triangle or the radius triangle. That means that the ratio of two sides on one triangle will be equal to the ratio of two sides on the other triangle. So writing that now, I'm going to look at the side that has the change in velocity and then just the velocity arrow down below. We're just going to talk about the speed now. One side is just the speed. The other is that change in velocity. And we'll drop the vector arrows because we're just talking about their magnitudes now. And that's got to be equal to the change in position over any one of those radius vectors. Now, what is velocity defined as? Velocity is defined as distance over time at a constant speed. So v over, let's see, the change in your radius over your time interval. And that's got to be equal to the change in your radius over your radius. So that's going to be, and we'll say that's because since speed equals distance over time at a constant speed. Remember that equation doesn't apply if we're getting faster or slower, but we are not getting faster or slower here. Rearranging a little bit, what we're left with is, oh no, I messed this up. Dang it, I'm going to back up a little bit. What I said is true, but it doesn't get me where I want to go. What I want to say is it's similar. So back up. I apologize for the mistake there, but what I want to say is at a constant speed, distance equals speed times time. Again, only for a constant speed, which we do have in this case. And I don't want to change the left-hand side of the equation. Instead, I want to turn that change in position, the distance, into something that says speed times time. There we go. We're back on track now. I'm going to multiply this v over to the other side. And what we get is that the change in velocity is equal to speed squared times time over the radius. And now I'm going to divide the time over to the other side. And what we have is the change in velocity over time. That must be equal to the speed squared over the radius. And what is this quantity? Change in velocity over time? Well, that's our definition of acceleration. Therefore, acceleration in the radial direction must be equal to speed squared over r, or its magnitude anyway. And then its direction is going to be toward the center of the circle. Why is the direction toward the center of the circle? Because that's the direction of the net force. And the net force and acceleration must always be in the same direction. All right, so there's our derivation of that equation. Nice geometry principles at play.